Hey there, welcome to this explainer. Have you ever actually stopped to think about how complex software makes its decisions? It's kind of wild when you think about it. Whether you're logging into some massive multiplayer game, streaming a movie, or, I don't know, literally routing a rover on Mars, all of those incredibly layered decisions, they all boil down to just simple true or false questions. Seriously, today we're going to master the flow of software by figuring out exactly how those true or false questions combine to create some really incredible logic. So let's just dive right into this. Here's a quick roadmap of what we're covering. We'll start with combining Boolean values, then map things out using truth tables. After that, we'll look at preventing crashes with something called short-circuiting. And finally, we'll wrap up with De Morgan's logical laws. Okay, kicking things off with Section 1. Combining Boolean values, the building blocks of logic. So a single comparison, like asking if someone is 18 or older, gives us exactly one tiny piece of info, true or false. But real-world decisions rarely depend on just one thing, right? That's where logical operators come in. Let's look at the AND operator first. The AND operator strictly requires both conditions to hold up at the exact same time to be true. Think about it like a roller coaster rule. You can board the ride if you're tall enough and your harness is fastened. If you're tall enough, but your harness isn't clicked, yeah, you're not riding. Harness is clicked, but you're too short, still not riding. Both of those things literally must be true together. If even one is false, the whole thing is false. Now let's contrast that with the OR operator. This one returns true when at least one of its operands is true. We call this an inclusive OR. For instance, say you qualify for a discount if you're a student or a senior citizen. If you're just a student, boom, you get it. Just a senior, you get it. And hey, if you happen to be a student who is also a senior citizen, you still qualify. Just one condition needs to be true to satisfy the whole requirement. It's only going to return false if both sides are completely 100% false. Now, I want to point out a visual difference here because this is a major trap for new programmers. In Python, logical operators like AND, OR, and NOT are always written in lowercase, always. But in AP's pseudocode, they are strictly uppercase. Capitalization matters so much here. If you're coding in Python and you accidentally type a big uppercase AND, it's going to throw a name error and just crash your program. So yeah, always keep your Python logic lowercase.
Moving right along to Section 2, mapping with truth tables, systematically listing every possibility.
Now that we've got a handle on those abstract operators, we need a systematic way to map out exactly how a computer processes every single possible input. So what is a truth table? Well, it's basically just a grid that enumerates every possible combination of Boolean input values and what the resulting output would be. Think of it as a totally complete, unambiguous cheat sheet for any Boolean function. Because it literally lays out every single scenario, it's our absolute best tool for checking if two logical expressions are truly equivalent. Let's look at how this works in practice. Notice how this grid mathematically plots out that exact roller coaster rule we talked about earlier. We've got our inputs, A and B. Let's say A is being tall enough and B is the harness being fastened. Take a look at that output column. The output is a 1, meaning true, only in that very last row where both A and B are 1. In every other scenario, because one or both conditions fail, the output is just a big fat 0. Now compare that with the OR gate truth table. Look at how totally different the output column is here. The OR gate only spits out a 0, or false, in that very first row where both operand A and operand B are 0. Everywhere else, because there's at least a single 1 in the inputs, the output is a 1. It's a perfect visual for that inclusive discount rule we mentioned. Okay, let's test your understanding real quick with a classic AP exam question right from our source text. A truth table for an expression with 4 Boolean inputs has how many rows? Take a second to think about how that mathematical scaling actually works. Got a guess? The answer is 16. And here's the trick to figuring that out. Because each input can independently be a 0 or a 1, false or true, right? You just use the rule of 2 to the power of n, where n is your number of inputs. So 2 to the 4th power gives us exactly 16 distinct rows. Pretty neat, right? Now, if you ever need to build a 3-input truth table yourself, you can do it without missing a single combination if you just follow a simple system. It's almost like a rhythm. Start with your rightmost column and just alternate 0, 1, 0, 1. Then move over to the middle column and alternate every 2 rows, 0, 0, 1, 1. Finally, that leftmost column, it changes every 4 rows, 4 zeros, then 4 ones. Doing it this way creates a perfectly logical, organized pattern that guarantees you cover all 8 possibilities. All right, moving on to Section 3, preventing crashes with short-circuiting, a programmer's secret weapon. This concept right here really is a programmer's secret weapon. We're moving from theory into a supercritical practical application, literally stopping a system crash before it even happens. Imagine you write this piece of unsafe code. If user.is logged in, print welcome. I mean, sounds completely logical, right? But wait, what if that user object doesn't even exist yet? What if it's currently set to none? Well, if you run this, your program instantly crashes with a fatal attribute error. Calling a method on a none object is a massive, very real headache in software development that completely ruins the user experience. But now, look at the safe version of that same idea. If user is not none and user.is logged in. The really crucial point here is how this safe code actually prevents that crash. You see, Python evaluates compound Boolean expressions from left to right. And thanks to a really clever feature called short-circuiting, if that very first condition fails, Python just stops evaluating completely. It throws in the towel right there. It doesn't even bother looking at the second half, which means that dangerous method is never actually called on an empty object. Crisis averted. Let's detail exactly how Python knows to skip those unnecessary evaluations. There are 2 specific short-circuit rules you really need to remember. First, for an AND, short circuit, if the left operand is false, the entire statement is absolutely guaranteed to be false no matter what, so Python just skips the right side entirely. Second, for an OR short circuit, if the left operand is true, the whole statement is already a guaranteed true. So again, Python completely skips evaluating the right side. It's super efficient. To prove why this really matters in the real world, check out this safe math equation. We're setting a result to check if x is not equal to 0 and 10 divided by x is greater than 2. Now, if x equals 0, dividing 10 by x would normally trigger a total program killer, the zero division error. But because x is not equal to 0 instantly evaluates to false, the AND statement short circuits. That dangerous division is completely skipped over, and the program safely evaluates to false without crashing the whole shebang. And that brings us to Section 4, De Morgan's logical laws, bending the rules of logic. We've hit the most advanced part of our explainer today, building on basically everything we've talked about so far. These laws are 2 formal logic rules created by Augustus De Morgan, who was a brilliant 19th century mathematician. They describe exactly how the not operator distributes across and OR statements. Understanding De Morgan's rules is absolutely crucial, not just for writing really clean, efficient code, but honestly, it's also a major, frequently tested skill if you're taking the AP exam. Let's break down his first law. It states that not A and B inside parentheses is logically equivalent to not A or not B. Look closely at what just happened there. As that not operator gets distributed inside the parentheses to attach to both A and B, it actually actively flips the AND directly into an OR. It's like mathematical magic. And the second law is basically just the exact inverse of that scenario. It states that not A or B inside parentheses is logically equivalent to not A and not B. Once again, as you distribute that negation across the elements inside, the OR flips right back around into an AND. Look, if you take away just one single phrase from this whole advanced section, please let it be this exact quote directly from our text. When you push not inside the parentheses, the operator flips. That's it. It's a super easy to memorize central rule that will honestly save you time and time again when you're staring down some really complex compound conditions. To wrap up our explainer today, I'm going to leave you with this final provocative AP exam check directly from the source material. Which 2 expressions are equivalent to not A and B? Think carefully about De Morgan's laws, how that not operator flips the logic, and how you could systematically use a truth table to prove it to yourself. Apply what we've just covered, dive into the combinations, and see if you can crack it. Thank you so much for joining me today, and keep mastering the flow of software.